recording here. And for your class, the 130 class, second semester, you know, it's very similar to your first semester test. The difference is you're taking it next week. You'll need to connect with your instructors to find out what day that is for you, because I don't know that. All I know is, you know, what we're preparing for here. So again, if anyone has any questions, please put them into the chat box or unmute yourself and just let me know what questions you have from the practice test. And if you're just now working through the practice test, that can be also why you don't have any questions. So just go ahead and if you want to look ahead, and if you see anything in there that looks puzzling, let me know and I'll work it out for you. We're going to do questions 17, 18, 19, and 20 on the practice sheet. So question 17 deals with a patient must receive a tube feeding of NUR 120 milliliters in 90 minutes. Calculate the flow rate in milliliters per hour. So we know that we have 120 milliliters and we need to give it to them within 90 minutes. And we need to calculate flow rate, and we can do this in a couple of different ways. I'm going to show you the dimensional analysis way. This is the surefire way to get it right, because you know, it takes all the guesswork out, unless you obviously don't know how to do dimensional analysis, which can be the case. But what I've done here is I converted minutes to hours. So we know that 60 minutes, 1 hour, and that would give us one answer. Another way is just to convert the 90 minutes into 1.5 hours, because what is 90 minutes? It's an hour and a half, right? So if I do 120 times 60 divided by 90, I get 80 mil per hour. So that's 17. 18. 18 states that we have an order of 0.9% sodium chloride, 500 milliliters IV, infusing at 125 milliliters per hour. And we want to know how long will that infusion take. So I start off with my 500 milliliters. And in order to calculate the infusion rate, again, I'm just going to use dimensional analysis. I can convert milliliters to hours because I know that the infusion rate is 125 milliliters per hour. If you just took 500 divided by 125, you're doing exactly the same thing I'm doing. I'm just writing it out differently. You set it up the same way. This infusion will take 4 hours. Again, I write this way because Then I can eliminate my units and I'm left with just the hours. So I know I've set it up correctly. You can see that there's a variation of this question. This is actually from the 4th semester class. They had 420 cc's infusing at 120 cc's per hour. And then the question said, what is the hours and minutes for this running out? The answer was 3.5 hours. So you would write out 3 hours and 30 minutes. For if you happen to get an answer of 3.25 or 3.75, then 3.25 is 3¼ hours, 3 hours and 15 minutes. 3.75 is 3 hours and 3/4 hours, or 3 hours and 45 minutes. That's why that was written up there from earlier. All right, 19. 19 says the patient is to receive 375 milliliters Ringer's lactate over 3 hours. And then what would we set the infusion pump to? So 375 milliliters, 3 hours. And we're just going to do 375 divided by 3, 125 milliliters per hour. Believe it or not, this question 19 is commonly missed. And the reason it's commonly missed is because you guys might be looking for more math to do. The only math here is just to reduce 375 divided by 3. That's all I did to find out the milliliters per hour. Okay, so there's nothing to multiply or necessarily divide by that's outside of the flow rate, which is just volume over time or milliliters over hours. And then finally 20. 20 is the physician ordered 1440 cc's of dextrose 5% normal saline to be infused over 12 hours. If your tubing is labeled as below, what will the flow rate be in drops per minute? Now, this is I think this is new for you guys this semester, but in order to calculate drop rate, I need to know 2 pieces of information. I need to know the flow rate, and I need to know the drop factor. When I know those 2 pieces of information, I can calculate my drop rate. Okay, so it tells me already what the flow rate is. It says 1440 cc's, 12 hours. It tells me the drop factor, which is listed on the label, is 10 drops per milliliter. So on your practice sheet, you have that big number 10, and then written underneath, it says 10 drops, approximately 1 milliliter. Now, drop rate is supposed to be in drops per minute. And so we have hours right now. So we need to convert hours to minutes. Now you can do this a couple different ways. You can write this out and then add a separate conversion factor, which is what I think I'm going to do to show you. Or from the get-go, you could just convert hours to minutes. So 12 times 60 is 720. Or you can reduce 1440 over 12, which is 120 cc's per hour, and then convert hours to minutes. 1 hour equals 60 minutes. But just to stay consistent with dimensional analysis, not that any of you asked for that, we can convert hours to minutes. 1 hour, 60 minutes. And then when I do this, you'll multiply across 1440 times 10, then divide by 12, then divide by 60, and then you should get 20 drops per minute. Any other questions from the practice test? Or any questions about the format of the test or anything like that? You're welcome, Sylvia. Okay, so 21. Once I find it here. So 21 says that an order requires 60 milligrams of a drug to be administered intramuscularly stat, the vial has the following three choices of strength after reconstitution. So 5, 10, and then 20. And the question is, determine the volume in milliliters for the strongest concentration. So our strongest concentration is going to be 20, because 20 milligrams per milliliter means you have 20 milligrams of that drug in 1 milliliter. So 20 is greater than 10 and then greater than 5. So what we're going to do here is take our order. So this is number 21. We're going to take our order, which is 60 milligrams, and we're going to convert milligrams to milliliters. 20 milligrams, 1 milliliter, and then your answer is 3 milliliters. Now, if you do ordered over half, the way that would be written out is this: 60 milligrams over 20 milligrams times 1 milliliter would give you the same answer, 3 milliliters. So if you don't like dimensional analysis and you're doing this, that's fine. As long as we're getting the same right answer, then we're all on the same page.
Thank you.
You're welcome. Question 23, you probably already know how to do. It's just that the way it's organized or the way it looks just maybe looks a little bit different. But basically all you're going to do is you're going to find the milliliters of the visceral, the milliliters of the meperidine, and then add them together. Okay, so let's work it out real quick. So for 23, visceral ordered is 60 milligrams, and then available is 50 milligrams per milliliter. And then for the meperidine, ordered 85 milligrams. And then the available is 75 milligrams per milliliter. And 60 divided by 50, I believe, is 1.1. Check that. 1.2 milliliters. And then 85 divided by 75 gives me 1.1333 repeating. And we're going to go ahead and round that to 1.1 milliliters. Okay, so you want to round to the nearest tenth. Then I'm just going to add these two together. Just going to add them together, and I get 2.3 milliliters as my answer. So that's how much you're going to put into the injectable and then inject. All right, so question 6 on the practice test. Always a fun one when we talk about fluid replacement volumes and urines in the question. So I'm going to show you how I solve this, which might be a little bit different than how you solved it, but as long as we get to the right answer, we're good. So it says for every 125 milliliters of urine output, you're going to replace with 40 milliliters of water via the PEG tube. If urine output is 500 milliliters, then what would we replace the volume with? So I do it. This is the way I solve this type of question. Any kind of fluid replacement questions that are similar to this, I'm going to take what the actual output is. So the 500 milliliters was the actual urine output over that initial expected output, which was the 125 milliliters. And then I'm going to multiply by the replacement volume. Now notice everything has a unit of milliliters, which is why I'm hesitant to, mention this from the standpoint of dimensional analysis. But if you take your final output over your expected output times the replacement volume, that's essentially the formula that I'm following. And when you do that, you'll get what is it? I think it's 160 ml, but let me just double check. Yeah, 160 ml. Another thing to keep in mind, and there's a couple of different ways you can rationalize or reason through this type of question. So for every 125 milliliters lost, we need to replace with 40. So you know that it's going to be a number greater than 40, right? Because 500 was the actual lost. And so you know that number is going to be less than or more than 40, because obviously we would do that. So for every 125 milliliters lost, it's 40. So 125 times 2 is 250, 80 milliliters. Times 3 is 375, 120 milliliters. And then times 4 is 500 milliliters. And that's where we get our 160 milliliters. So just, you can use a variety of different ways to kind of rationalize or figure this out. But this is what I have found out to be helpful, at least for me, is I take the actual output over the what I consider the theoretical output or the expected output times the replacement volume, and that'll work every single time. And all three of these numbers could be different. As long as we follow the basic formula, you should still come up with the same answer.